Dovrebbe essere gas, spanning. Spanning non conosce gas. Sì, solitamente sì.
Ai suoi tempi. No, people. No, questi sono. Vabbè, quando si connetteranno gli altri. Allora, visto che siamo solo noi, io intanto vi dico che sto malissimo, veramente mi sento anche la febbre. Comunque, non sarà.
Adesso andiamo via anche noi.
Ce la faremo. Ok. So for those connected online, can you see the screen and hear my voice?
Yes, it is clear.
Okay, perfect. Okay, so let's start like this. Display settings. Perfect. Before starting, as I was just saying to somebody of you, for those who are attending in person this course, next lecture will be on the use of the console multiphysics software. Well, I actually cannot connect to the server, to the license server, storing the licenses for this console software. So my problem is that I would like you to use it to see some simulation running and so on, and above all to run some experiments. So if it's not a problem for you, next Monday, can you come at my laboratory in Via Mendola at, let's say, 3 in the afternoon and take there the lesson?
Monday?
On Monday.
Oh.
So
yes.
This Monday there will be the third lesson, right? Instead of doing this here in this class, we can do that in our laboratory.
Yes,
That's not a problem. Okay. I just need your names, but I think that those that are on this paper are your names, right? So just to say the security people that you are coming, and they will recognize you and let you in our department. But anyway, once you are downstairs, you arrive at our laboratory. Now I will give you the address and or send you a mail with Google Map position. It's very close to here, so next to the administration of Poliba, right? And so this is for the attendance. For today. And as I said, once you are there, you arrive, you can send me a message on Teams. I will go downstairs and bring you up to the laboratory, right? Okay? Let's say at 3. So we'll see something about the lecture and then move to the laboratory to stay there and try to make some simulation. I think that is better for you to put your hands on this software. Okay. So this lecture is for non-destructive testing techniques. Just a brief introduction to the state of the art of what is used so far for non-destructive testing. And the idea, this was a panel from the previous lecture. So the idea is to here present you something about the experimental way to make testing of materials or complex structures and so on. To start with the experiments, just to say, okay, there are many ways to perform some experiment for quality control assessment, material assessment, and so on. And then focus our attention on thermography, which is our aim. And for any of, for every of these experimental ways to make some quality control of materials and structures, we will see the pros and cons, and then compare it with the standard, which is, for example, in industry, ultrasonics, typically, and thermography, which is what we want to study in this course. The other two blocks for experiments, let's say simulation tools, we will see on Monday, and then data processing the rest of this course. So let's start with the motivation. Motivation is something that I think is somehow straightforward to understand. So everything needs a quality control, an inspection that can be done during the production process or during operation. Let's say that in this case, it's much more related to maintenance problems instead of quality control as it is at the end of the production line. So during operation, what can happen? So first of all, aging. So the material your material structure, your complex structure, whatever, can alter its properties, both geometrical or physical, because of aging. This is something that is typically assumed. But also, for example, if you imagine an aircraft, and you need to inspect every month, every time that is needed, because of there's an impact with some foreign body during the working operation, there could be a damage due to this impact, or something like, for example, the corrosion for those materials like iron, let's say, that can be altered by the environment. Okay, and this is, for example, important for trains. So there are many parts of trains that are made of some alloy that can be altered by the effect of the environment, and so weather, for sure. During production process, so the first column, this one on your left, is what can happen because of, in general, because of, for example, there's a material that is altered, a bulk material that you use is altered because of, there are many, I don't know, foreign bodies within the material, of the properties, let's say the porosity, the expected porosity is not the same of the data sheet. Or there could be some production mistakes that are due to many causes. For example, an alteration of the parameters. This is the third line, the wrong parameters. So, for example, imagine you're making some robotic welding of your of a joint made of an alloy, let's say aluminum carbonate. Okay, and once you get this, made, for example, a laser welding. So you know that there are many parameters. For example, the current of the laser that is creating the welding pot, right? this should be something that is controlled in a closed loop. But there could be, I don't know, some event that is altering this current, even because of the target itself as something, as an impurity within the material. So, and you are not able to control this drift of the current. And then you say, okay, my laser welding is working fine because I see there the current is of 3 amperes and it's good. But actually, the actual current that is driving your welding is different from 3 amperes, and this is something that could happen, even if your closed loop say that everything is working fine. Or human errors that are typical of manual productions. So, and you can imagine how many errors a human can make. And for the second column, these are much more related to composite production. As I told you 2 days ago, when we work with composites, typically there's a process of lamination. So you start with some layer, then add another layer, let's say tilted of some angle to reach the structure of your composite. And you can get, for example, inclusion of materials, delamination, that is something typical of the joints, or there will be some geometrical error due to an error of this stratification that you made within using your taper. That is something with a finite weight of about 150 millimeters. Or also the porosity could be altered for effect of the final process within the autoclave, where there's a polymerization of the polymer that you are using for making the constituent of your composite material. So let's say that testing is important in aeronautics, for example, which is our domain in this case, to prevent catastrophic consequences. Anybody want to fall down with your airplanes or with your aircraft? But in any case, we don't want to waste time and money. But this was, as I said, Industry 4.0, but there's also another point driven by the environmental problems and so on, to increase the sustainability of the production. Testing could be destructive or not destructive. So destructive means that you are making your test, and in some way you are altering the physical and geometrical properties of the target that you are testing. For example, this could be very useful during the design of your structure. Because, for example, if you are designing a joint that will be a piece of a wing of an airplane, maybe you are interested to see which is the stress, the maximum stress that this joint could suffer during its working condition, and then to get some feedback in your design to improve, for example, the structure, to add much more layers or change the geometry. So this is made typically with destructive testing, fatigue test, and so on. And let's say that you want to estimate, for example, the life of your components subjected to some severe conditions, weather conditions, or for example, if you want to test your the resistance of your structure, not for what is designed for. Let's say that you are making some structure that should take a static weight of, I don't know, 1,000 kilos, right? You can multiply this weight by 10 and try to test the same structure with under this condition to be sure that your structure is able to resist to this static weight. Non-destructive means that you have already designed, so you know what to expect. But you are taking care of all the problems that could be arising during the production process. And you want to test all the products. And once the product is tested, you say, okay, this is fine, this is good, you can pass it to the market. So the properties are not altered by the test itself. And you can, of course, sell your good and be sure that everything is okay for what you expected, for what you designed. So in destructive testing, there are many ways to perform testing. For example, as I said you before, aggressive environment testing under some weather conditions, or corrosion testing when you put your target within some material like fresh water, seawater, depending on the environment that typically you are supposed to meet. Not you, of course, your structure is supposed to meet during this working condition. Or fatigue testing, fracture and mechanical testing, and residual stress measurement. For example, this last, so for fatigue testing, for example, is typical, as I told you before, for welded joints or joints that are not welded with adhesive points within two structures, just to be sure that it's able to manage some loading to your joint, and then try to understand how you can improve your joint. Or also, once you get a crack, there may be something that could happen even in working condition. For example, let's say that your aircraft is bumping, for example, a bird. It's kind of something that could, well, it's not so typical, but it's something that could happen. So in this case, there would be a crack, for example, and you want to be sure that your crack is not going to grow to damage the whole structure. And you can simulate this condition during fatigue testing. Residual stress measurement is another way to improve your design. So once you get a stress and then you remove the cause of your stress, you can then measure the stress that is residual to the structure, and then try to decide some way to keep out this stress of your structure, or improve the structure to be able to manage this stress, this residual stress, even if there's no other cause that is creating this stress to the structure. So regarding the pros of destructive testing, it is clear that you can make a lot of measurement. You can even measure direct strengths, fracture strengths, elongation, modular elasticity of the structure, not of the bulk material, so what you see from your data sheet, but from the last part, from the finished object, so from what you have designed and realized. And then it is very important, as I told you before, to use this technique during the design of your object, of your complex structure. You can simulate everything, almost everything, even with COMSOL. We will see in the next lecture. You will be able to simulate the stress, thermal sources that could alter your structure. But at the end of the story, the best measurement that you could do is, of course, made on the actual final object that before you are going to sell it, to place it into the market. And then the destructive testing also give you a kind of prediction of what could be the typical failures that you will meet, that your structure will meet during this working condition. In non-destructive testing, there are many other pros for sure. So you can test whatever you want, because you are not altering the structure, and you can test whatever you want, but you cannot make the same assessment that you can do for destructive testing. Typically, in non-destructive testing, there's a kind of indirect measurement that you made of your parameters of what you want to understand. But it is much more important to use non-destructive testing at the end of production line, because this makes you able to find possible defects, the ones that we have seen before that could be made due to many causes that are in any case or in any production line that could arise. So let's start with the state of the art of non-destructive testing. So we will focus on non-destructive testing because our aim is not to design products, but to be at the end of your production line and then to understand the defect, whether there's a defect in your object. We can cluster non-destructive testing into main groups. So for the detection of surface flows and for the detection of internal flows. For surface flows, typically we use visual inspection, that could be manual or automatic. We use, for example, magnetic particle inspection and dye penetrant inspection. In case of internal flows, we can use, for example, X-ray, ultrasonic testing that, as I told you before, is somehow now considered the standard, and there are also some ISO specifications for ultrasonic testing, eddy current testing, and finally our active infrared thermography. So for visual inspection is maybe the first solution that we can use. By means of your naked eye, you can state if there's a flow, for example, on your component. What the problem? That naked eye can suffer from. You can be tired, for example, or you cannot be able to see something within the material for sure. But using some instruments, some very easy equipment like magnifying glasses, light emitters, and that's what is done in Bridgestone for the tire control that I showed you 2 days ago. You can, of course, we are not in the pre-digital era, but they are almost in this era of before the use of cameras, of digital cameras. But you can identify defect with your naked eye, but with many problems. Most of all due to your to something that is subjectivity. So there's no way to assess the objectivity of a measure made by humans. Okay. Today, so everybody has more than 4 or 5 cameras in your pocket. If you think about it, it's the truth. And maybe we can take advantage of these cameras and try to make something smarter using digital cameras to collect images and then try to produce something, let's say, as we said last lecture, produce something with artificial intelligence that is able to classify your images and state whether or not you have a surface defect on your structure. Or you can even produce 3D data for the geometric assessment of what you have done. For example, the 3D inspection can be done with many ways. So 2 days ago we saw stereo vision, for example, but stereo vision is actually not very used in industry. because the resolution of stereo vision systems is very, very low if compared with other strategies. Let's say this one with the structured light or laser profilometry. In stereo vision, you typically can have a resolution of 1 to 10 millimeters, while with this structured light system, or also with laser profilometer or time of flight cameras, you can get you can go below your millimeter, so you can get much more accuracy for your and more than accuracy, much more resolution to your measurement. In structural light system, that is very easy to understand how it works. There's a pattern of light, so there are some bands, white stripes and black stripes that are projected onto some surface. Then there's a camera that is collecting these stripes here and try to understand the width of any band that you project. So when there's a jump in the depth, for example, here there's the nose, or here close to the here, you can see that the jump, the band, the black band is much thicker than what you have, for example, on a flat surface on your cheek. Okay, and then you can reconstruct, starting from the analysis of the thickness of these bands, you can reconstruct with a good accuracy and a good resolution the 3D shape of your object. So the problem here is that you need to move, so you can collect 3D points from the edges of your bands, only from this point. So you need to move your setup or move the projection of your light. So instead of projecting normally, you can tilt your projector and illuminate other places. Or another way is to encode your bands and change the thickness of your bands. So changing the thickness means that you are moving the edge. That's the actual point, the actual line where you can derive your 3D points. Is it clear? So maybe from this image could be also better. So for example, the nose of the elephant now here can be, can you see the mouse? Okay. So here is detected from this line, but if you change the frequency, the period of your bands, you can illuminate other points of the nose of your elephant and simulate the movement of the whole setup, keeping everything in the same position. There are other cameras that are very, very smart for 3D inspection. For example, time-of-flight devices. In time-of-flight devices like this one is Microsoft Kinect V2 that was first released for working with the Xbox V2 console for playing. And it works. Typically, we have a light projector that is illuminating your, typically working in the infrared, so in order that you cannot see it for sure. And then just modulating the amplitude of what you are emitting, you are able to detect the time required by the light to touch your target and go back to the sensor. Then, knowing the amplitude, how it is modulated in frequency or even in amplitude, you can estimate the phase, that is the phase of what is returned to your sensor, and then phase means delay. Okay, estimate this delay, and once you have this delay, from very easy formulation, get the time of the round trip to touch the target, and then estimate the depth of the distance, it's much easier to understand the distance of the depth from the central point of the camera. And there's a very important advantage in this case, that you are able to get millions of points per second. And this term millions depends on two specifications. The first one is the frame rate of your camera. For example, standard camera are able to make to have a frame rate of 30 frames per second. This is a typical frame rate of your camera of your smartphone, for example. But there are many other cameras that are much faster. They can reach also 200, 500 of frame per second. And for each frame that you are able to collect, the number of measurements, the number of points that you can collect is equal to the resolution. So if you have a VGA resolution, for example, you will get 640 by 480 measurement per frame multiplied by your frame rate. VGA resolution is something that is very low, but typically for this camera, since there's an infrared detector, is a good value for of resolution for these cameras. There are many other ways to make some 3D inspection. This is a Velodyne that is a sensor that, well, this one is very aged. Maybe it was a sensor of 10 years ago. And the first sensor needed a scanning mechanism. So you get just one point that was projected onto a mirror, and then you rotate your mirror to scan the environment, and then to understand the round trip of encoded by the movement of your mirror. But now everything works with some sensors like CCD and CMOS. The CMOS are much cheaper than CCD, but with lower quality of the image that you achieve. So in the problem of, there are many sources of error. For example, they could be random or systematic, and this is something that is typical of any sensor. So the one that you see here is a Microsoft Azure Kinect DK development kit. That is a camera that has been released, I think, two years ago, before COVID, so maybe in 2019, so more than 2 years ago, but was released only in the US and in Germany. But now it's available also in Italy, and you can use it to make some inspection. For example, the control that we made in Fincantieri, in the naval industry, that I showed you 2 days ago, was made with the Azure Kinect camera. So we just take this camera that is able to have a good resolution and a good accuracy of the estimation of the distance in front of the target, and then record images, and then to improve the results, just taking a patch, a region of interest of your image, and then see how it changes in the distance to get the deformation while the robot, let's say the robot, was welding the joints, the panels that are the constituents of your boat. And why we use, for example, this Azure Kinect camera? Because first of all, we are interested in geometrical inspection. So, and this geometrical inspection is something related to visual inspection. So you can inspect geometry just looking at the surface of your structure. And even if it is an active sensor, so there's a projector of light. You can use it while the robot was welding the structure, because welding produces an illumination for sure, and there's some smoke, etc. But the typical wavelength of this illumination are more at the lower band of visible spectrum. So how this works at near infrared, and we will see the difference between the spectrum later on. And all this illumination that affect the lower part of your visible spectrum, blue bands, green bands, are not affecting the infrared. That is where this camera works. So with the error sources, these are random sources that could be improved, for example, by time averaging, and it's something that we have made in this experiment that I showed you. But also other systematic errors. Maybe something very related to this camera is the multipath. So or the face wrapping. In face wrapping means that, as I told you before, you can estimate the distance by looking at the phase changes between what you emitted and what you received. So let's imagine that you are emitting something that is modulating in amplitude. Maybe this is much easier. Something modulating in amplitude by a sinusoidal wave. Then this sinusoidal wave go back to you, and you can estimate the phase alteration and say, okay, my alteration is of 90 degrees, and then from 90 degrees, estimate the distance of your target. What's the problem? That there's an ambiguity in the range of 0 to pi. Because once you are below some distance, you are not able to estimate, but you get some wrapping of your estimation of your distance to 0. So everything starts again from 0. And okay, so this was a problem of the first release of this kind of camera. Now, actually, there are many ways to avoid this problem, just taking account of the continuity of the world, of our surroundings. So it's not possible to have something that is there of 2 meters far from me and then 0 inside me. So of course, there are many ways to solve this problem by software. The other problem is, and this is not solutionable, is a range overestimation. So the camera is, so your pattern of light is projective as a plane wave that is flowing through your environment. So this means that you get multiple rays that are illuminating your environment. And when we are in this, for example, in the corner between two walls, there will be this direct. So let's say that you are interested to this path. So this is at a distance of 1 meter, okay. But then there's this direct path, and there's another path that is impinging on this wall, and then go back to wall A to the camera. So this path, of course, is increased of what we was expected by this term of the multiple path, the multiple reflection path. And there's an overestimation due to this multiple path while we are looking to something that has this kind of structure. This is an example. So what is brighter means that is farther, and in the corner you can get this problem. The other way to estimate, and is very important for industry, above all when you are working with something very small, is the use of laser profilometry. So in principle, you are emitting with some laser source, let's say a point, that might be easier to understand. You are emitting this point to the target that is placed at position A. Then there's, let's say, a movement or an alteration of the depth that moves this surface from A to B. And actually, if you are using a linear CCD, a camera made just of one line of detectors, your laser line, your laser dot will be detected first in this place and then in this one. Firstly in A and then in B. So this means that any alteration of the depth of the distance produces an alteration at a kind of disparity, like in stereo vision, in your CCD, in your CMOS matrix, whatever you're using for with your camera. Instead of using a dot, typically we use a line. So every line, in principle, well, there are many problems in what I'm saying, but in principle, if you are able to project your line perfectly orthogonally to your surface, you will produce so let's say that you have this structure that is in 3 dimensions, okay, and you are projecting this line. This is the laser line. When you see your camera, your image on your camera, you will see something like that, of course. So for any column of your camera, you will be able to detect a point. So every column, if we see the intensity, so because we know that an image is a matrix of intensity, so maybe if everything is black and there's only the line, this will be 0 in grayscale. This will be 255. You will produce, looking at this column and projecting it into rows and intensity, you will see something like this. Okay, so this point is this one. This point is the peak, because you get the maximum of intensity. Okay. If everything is perfect, is ideal, this will be something like a belt of Dirac. So you get 0 everywhere and 255 in a point. But because of your distortion, your lenses are introducing many problems to the reconstruction of your line. There's a kind of Gaussian shape. So you can estimate the maximum of these intensities and say that at column 100, at the row 250, you get the maximum of intensity, and then reconstruct with simple, and we see which are the formulation. With simple formulation, the change of the depth. So, because if everything was flat, you will see a line like this. So this point, this delta of rows is your disparity. So the same that you get when you look with the 2 eyes. So if you have your disparity, so this delta, you can estimate the height of your structure, or what you are trying to replicate in 3D and get your final scan. And there are many configurations that you can use. For example, there's a standard configuration where the laser is normal to the to your object, to your target, and take care of this alpha. This is the term that determines your resolution. So to get a higher resolution, you have to increase this term alpha. So you are able to detect very slight alteration of your 3D space onto the camera if this alpha is high. What's the problem? That if I am impinging with some laser source to this point, to this panel, if I see my point of view that is almost aligned with the laser, my resolution is the worst, and this is right. But I can get the maximum of the intensity because I'm close to the specular reflection of the laser. If I increase this alpha, this value of alpha, and I'm looking almost parallelly to this flat surface, my point that I'm impinging with my laser will be darker, much more darker, than because I'm far from the specular reflection. For these conditions, we typically use the specular configuration. That is the one that is able to maximize the resolution and at the same time to get the maximum of reflection to your camera. The problem is that when you work with specular configuration, you can get multiple reflections. Okay, so this condition that I told you before, that there's just one line in your camera could not be valid at all, because maybe there's another reflection here, there's something here, multiple reflection due to the structure. And this is very important when you work with metal surfaces. So if you extract this column, okay, here you get a maximum reflection of 255 of intensity. And this point, for example, is not proper, is lower. Your intensity is about 180 of intensity. I mean, the value of the pixel in that position. So maybe you can estimate at your point that your disparity is not this one, this interval, this small interval, but it's this one. So you are creating an outlier in your point cloud. So instead of having a representation of your panel perfect, you, nobody knows why, because of multiple reflection, you will get here some clusters of points that have been reconstructed because of your multiple reflection, that of course are not belonging to your surface, but are due to some problem that you get while making your acquisitions. And another important configuration is the look away configuration, the fourth. Why this is important? Because typically you can get some self-occlusions of your structure. For example, if you imagine to concave structure, not convex, but concave structure, maybe you are not able to illuminate your surface with the laser, but you need to tilt the laser to reach those points, and at the same time tilt the camera, because if we take the camera, for example, on the top of the surface, you will be not able to detect the laser. So it's invisible because of self-occlusion of the material, of the structure. So in laser profilometry, so for example, if you can remember, 2 days ago I showed you that experiment with the tools, with the drilling tools. This is the profile acquired using a camera from the side of a drilling tool. There was here a defect. This is something that is missing from this tip. And so you can imagine I don't know, I don't have a tool here, but on the side of your tool, we are just looking at the teeth. And then you can reconstruct this line. So okay, you're able to see. So for example, not everything is at 255, so in the maximum of exposure of this specific pixel. So you have to improve to have some way to reconstruct this line. For example, making line tracking. So this point will be next to this one, will be next to this one, and so introduce these conditions to reconstruct the line. But also, for example, once you extract this Gaussian shape function for the specific column, you can try to make a fit of this Gaussian function and make the central point of your Gaussian function, that is the expected value of your distribution, the perfect position of your point. So instead of having that this is 250, maybe the position, I mean, of the row where this pixel is light, you can get a sub-pixel resolution, because the expected value of the Gaussian can be 250.7248, whatever. Okay, I don't know if it is clear. You can improve your resolution with some software algorithm. Okay, and then also the width of this Gaussian width, this Gaussian shape function, can be a key performance index of your reconstruction, because it is clear that if you are over, you get the line, okay? If you are over exposed, you get some overexposure of your images, maybe once you reconstruct your line, you will get something that is much thicker than this, okay? And if you select your column, and pass to say like this, intensity and rows, you will get 0, 0, 0, and then something that is saturated for many rows to the maximum value of intensity. So this is something that we don't want to happen, because this means that you are increasing the width of your signal, and you are adding much more inaccuracy to your measurement. It's preferable to have something that this shape, even if we don't touch 255 of the maximum of the amplitude that can be detected by the camera. And
better to use a color camera or
it depends. It depends on which kind of camera you have. Camera can be, for example, can have some Bayer layer for so 1 pixel is made of 4 pixels with green. The typical Bayer pattern is green, blue, and red. So this is 1 pixel. If you use this kind of camera, you are changing the pitch of the pixel, because for example, you can say that I want this should be 7 microns, but actually it's double because of there's a pattern. It is better to use grayscale camera, monochrome camera, and if possible, a filter to the camera.
It's a configuration that
and also my suggestion is the polarizer. Because multiple reflections can be completely deleted by using some polarizer in front of the optics. So with the polarizer, let's say a circular polarizer, so you get the laser as a side polarization that is fixed because of the laser itself is able to produce this kind of light. But everything is reflected, change the secondary reflection, change the polarization, and just tuning the polarizer, you can, for free, delete these multiple reflections. And then, for example, in this case, there was an error in estimating the Gaussian fit, that is, let's say, the standard deviation of this profile, that was of 2.21 pixels. Everything is at sub-pixel scale, because we can use also decimals, even if we are working with indices. And there are many measurements that we can run, and this was just to show you the resolution that we can get in the distant measurement. Of course, in any case, so these are visual measurement done with light. So on the top of everything, there's the diffraction limit. Let's say that we are able to detect defects that are at least 10 times higher than the wavelength you are using. So, and that's why today the state of art of profilometers use blue line instead of red lines, because blue lines is at 400 nanometers, and you can expect defects of 400 by 10, so of 4 microns at least of size. So this is on the top of everything, the diffraction limit. If you want to go deeper and see something that has a lower size, you will change completely your configuration. Use, for example, an electron beam. So it's another kind of microscopy that is not related to visual inspection. Magnetic particle inspection is another way to detect surface flows. In magnetic particle inspections, first of all, we can only investigate ferromagnetic materials. So you can imagine here that you have your structure with, there's a flow here, there's a very small crack. And if you use a magnetic field to magnetize this part, there's a leakage on, these are the lines of the magnetic field, there's a leakage. And then if you spray something like iron powder or something like that, there will be a cluster of your magnetic particles on the top of your crack. And you can easily see, okay, there's a crack, you can identify your scratches or something that is not so easy to be seen visually by naked eye or with any other way. And this is an example of an instrument, of an equipment that is used for making this testing. So you typically induce a magnetic field, and but the problem is that, of course, magnetic lines have a very specific direction from one pole to the other. And you are only able to detect those defects that are normal to the magnetic lines. Okay, so how we can overtake this problem? For example, just rotating this instrument. So creating a let's say something that is rotating circularly, and then to also check for any direction of the possible flows that you get on your surface. This could be dry or wet, depending on the environment that you are using. The advantages, first of all, it's very simple to perform this kind of measurement. Just spray something on the top of your and then use this magnetic field to get the polarization of the material. But it is very fast. There's a problem that you are able just to, and you are able to detect also very small cracks because everything is magnified because of the powder that you put on your surface. Of course, there's a very important limitation that is due to the material. You cannot inspect everything, of course, but just for magnetic materials. And then in any case, there will be some case where you cannot use a magnetic field in your structure, because in this case, your testing is no longer non-destructive, but destructive. You can induce some polarization of your components. Let's say, for example, in the case of electronics, electronic boards, you cannot use a magnetic field for free, because you can induce something to the carrier of the semiconductor and alter the property of the semiconductor itself. In this case, it's obvious that it's no longer non-destructive, it's destructive testing. And then another problem is related to paintings. If there's a painting applied on the top of your surface, maybe this could change because of some clusters, some scratch of the painting and so on, or also the painting is not ferromagnetic, of course, made of plastic, say. So you have to remove the painting before doing this analysis, and maybe you don't have time to do that, or you don't want to do that, because in this case it's the destructive testing itself. Penetrant is another way to perform an inspection, a visual inspection. In this case, instead of the previous one, you can work with any material in this case. And it's very easy to make some analysis with dye penetrant. How you can do that? Typically, you clean your surface, first of all. Then you apply a dye penetrant, which is somehow a kind of painting to your material that is penetrating to the surface. Then remove it, ideally washing the material, but your dye has penetrated within your crack. Then use a developer on the top of your material, and then wait for a few minutes that your dye penetrant is developed by the developer, of course, and then you will get the final image, magnified image of your crack. So, for example, these are some sprays that are used in this case. So, for example, here you have already applied your dye penetrant, and then you need to remove everything. And once that you remove everything, you use your developer to get this, something like in this image, where everything is red, means there's a crack on your surface. And then you just need to remove your developer to get back to the initial, to the starting condition. And it's very, very easy to use this dye penetrant. It's very effortless and it's very cheap, because this spray cost as a cost is very, very low.
So what is the layer to cover the layer?
In what sense?
You show the picture to cover the layer after
where?
The fifth one, fifth.
The developer means because you want to have something that is larger, to want to see something that is brighter, okay? Before using the developer, you are just filling this crack of some dye penetrant material, but maybe the width, for example, of this crack is too small to be detected, even if there's something inside. The developer just extend this area in order to let you able to see that there is something there. So these cracks are much smaller than what you see. Because if these cracks were like this, maybe you can use your naked eye to detect these cracks instead of using some liquid, some painting to enlarge these cracks. And there's an important point, an important concept that is, of course, there are some safety requirements because you need to wear some masks and so on. But there's a problem that even surface roughness can alter results. And probably you don't need to have a surface that is completely flat in the sense of without any roughness. In italiano sarebbe lappata, però non so proprio come dire. And if your surface has some roughness, you can have problems because the dye penetrant is going within within your roughness, and everything starts to be like violet. Okay. And another problem is also related to the coatings, because maybe there's a scratch of your coating that is not properly a defect. That is something that is acceptable. But when you use your dye penetrant, this could be enlarged and could be seen as a crack and as a problem of your structure. Radiographic testing. Also, we are moving from something that is related to detection of surface flow to something that is related to detection of internal flows. So we cannot use visual inspection as it is, but we need to use something different to go within the material. And in this case, radiographic testing is very similar to what is done in medical environment. So you can use X-ray machines or some radioactive source, and the difference is related to the wavelength, of course, of the rays that you get. In X-ray machines, you get some larger wavelengths than in radioactive sources. Radioactive sources are able to penetrate much deeper within the material and can be used also for penetration of other materials such as plastics or oils or water, while X-ray machines are typically used for other kinds of materials like metallic alloys instead of water, because you know that the propagation of these kinds of waves is attenuated depending on the density of the material that you are meeting during your travel. And this is the principle, of course, as I told you before, it is the same to medical radiology, where you can see your bones by looking at something that is then developed. And depending on the path that the radiation is, which is traveling within the material, you can get darker or brighter areas on your film. In an X-ray tube is something like this, where you get a cathode and an anode. There's something here to protect the anode, so the electrons are moving to the anode. And then the anode has this specific shape with this cut here to get something outside the bulb through a window. Okay, and then so these are this is the cone of the rays that are produced by the X-ray tube, and there's a film that is made of silver bromide typically, that is then developed to understand if there were an exposure of these silver bromide particles on the film to the X-rays. And so these are the difference between X-rays and gamma rays. So with gamma rays, you are able to have some equipment that is much smaller in size, and you can also test many components because there's a deeper penetration of the rays with high penetration power and so on. With X-rays, the equipment is much larger, but and you can typically inspect something that has a thickness. Well, here I found this number 62 millimeters, but it depends on the target, on what you are inspecting, if it's an alloy or something like that. You can use gamma rays, as I told you before, also for inspection of materials that are, for example, immersed in oil. And then once you get your final images, you can also apply artificial intelligence, for example, to detect cracks. That could be here, for example, because there's a difference and there's an anomaly between what you expected, that is this shape here, and what you get from your inspection. It is something that is inside the material that you cannot touch with your sight. Okay. And okay, there's not the problem of for example, the magnetic particle inspection, where you need to rotate because you can detect any kind of crack, even transverse crack or longitudinal crack, if we are looking, for example, to a welding between two different panels. For sure, the most important concept of this technique is the health hazard. So you need to take care of some safety requirements to be sure that everything is in a controlled environment. And typically this makes this technique not suitable for automation. So just for specific consumer required, let's say, analysis of the parts. Maybe this is a kind of, even if it's a non-destructive testing, is used for making what destructive testing do. Okay, so for designing purposes, to make a small number of inspections just to get other information from your tool. Eddy current testing is another way to get information from some material that has to be conductive. Why it has to be conductive? Because we use electromagnetic induction. So with a coil here, you create a magnetic field that inducts something on your conductive material that is a current with a circular shape. These are Eddy's current. And you can also probe your current and the amplitude, the frequency. There are many things that you can see from your Eddy's current. Depends on what is the current that you are using as an input, for sure, so from your sources, then from the relative position of your coil and the conductive material that you are testing, but also from the specimen properties, so conductivity, permeability, the shape of your, in this case it's completely flat, but it's less a peak, for example. You can get some other distribution of the Eddy's currents, and finally it could depend from on defects within your conductive material. And there's another point that this non-destructive testing technique, NDT technique, can also be used for making conductivity measurement. Maybe as this is a conductive material, maybe you are designing something that has to conduct some current or something like that. And also for the for coating thickness measurement. So let's say that you are let's say making a process for the deposition of some primer that then is used for whatever in your process. So you want to check your primer thickness to be sure that you are making the deposition of your primer as good as possible. And you can use eddy current testing to check this thickness and be sure that you are respecting your tolerances. And for example, this problem of the primer deposition is very important in a naval field, because in this case everything is made more or less of iron, okay, but everything has to go in seawater. So there's a problem, of course, and you need to use some primer before your painting to protect the panels that you are using during your process in your boat. So
we use this any material or ferromaterial or
this primer.
No, the material we use for testing.
The material.
Because adhesives have thermal properties.
Yeah.
Then we use it has high frequency adhesives.
You say while doing. I can understand what I say. So while doing the test, yes. There could be a problem in the temperature, yes. And this is the con. So you need an equipment calibration before testing your structure. Well, actually, a calibration is something that you always need while using not only eddy currents, but for example, also ultrasonics. So you need something that is certificate, and you test your technique with the parameters that you decided for that specific technique to something that is certified. There are many ways to certify, for example, buying something that is a calibrated specimen, for example, but also producing something that is that has an internal structure that you are completely know because you have already tested with some other technique that has been used. So you need the equipment calibration for this problem. This is a problem also for the thermal inspection, because, for example, we will see later, when you are using some thermal camera, you are assuming that the emissivity of the target is something that is fixed. So you can set the emissivity, expected emissivity of your target. Let's say that it's a black body is equal to 1, but it's not obviously something that is related to the real world. So you need to calibrate or use some painting even to create a reference for your emissivity. So you need to pre-calibrate your equipment before doing the experiment. Okay. And now sonic testing. Sonic testing is something that I didn't expect, but it's used in Bridgestone with the tires. So there's somebody that slaps the tire, and then just hearing the sound is able to say that there's a problem within the tire itself. For example, if you throw to the floor something that is a bulk structure, maybe you will get a dull sound, bong. But if there's a void inside the material, the sound could be different. So hearing the sound can give you some information about the presence of defect. Of course, you are not able to characterize the defect, but just to have a first introduction to the possible defects that you can get in some materials. When we move below 20 kilohertz, we are working with ultrasonics. And ultrasonic testing is maybe, I'm quite sure that is one of the most important NDT technique that is actually used in industry. I've seen it in aeronautics, in railways, in naval industry. When you are making some structure that is very huge in terms of size, typically they use ultrasonic testing. There are many certifications, ISO certification for ultrasonic testing, and it's typically used for this kind of inspection. In how it works, it is very easy to understand how it works. There's a probe that is creating some way, an ultrasound wave within the material, and then this wave flows into the material, and go back once you touch, as in time-of-flight cameras. Once you touch, for example, the back interface of your finite structure. Then goes back and you will get an echo of your signal. Okay. If there's a defect within the material, and of course, the time at which you will get this echo, it depends on the space traveled by the wave. If there's a defect within the material, then there's a discontinuity, of course, and the sound that go back to the probe earlier than what expected. So you will get an echo within your A scan, and then we'll see what is an A scan. A peak of the ultrasonic wave within due to the presence of this discontinuity. There's a problem that, of course, discontinuity can be done because of the structure itself of the material. In this case, this is a very easy structure, but there could be, for example, I don't know, some welding, something that has a more exotic structure, and you need to be able to discriminate between echoes that are due to the actual structure and echoes that are related to the presence of the defects. And this is what I was talking about. So when there's a crack, so let's say that you are probing your material with something that is this piezoelectric transducer that is able to generate a normal wave. Okay. So at time zero, the receiver airs the here at the transducer itself. So this is almost equal in the saturation area. Then this is what we expected because there's a back surface, but there's a crack, and you will get something that is lower in the amplitude of the signal that you received, of course, but there's something. This means that you have touched your crack, your discontinuity within the material. And there are different ways to make some setup. For example, there's a transmission setup where the transmitter and the receiver are from different sides of your target. This means that this initial pulse is equal to 0, because at time 0 you are not able to hear any ultrasonic sound within the material. The problem is that it's not always possible to take something, a transducer and receiver, and apply on different sides, because, for example, you are not able to reach one side, one surface of your specimen, or you are not able to guarantee that they are perfectly aligned. And okay, we see later in the reflection setup, this means that there's a peak at time 0 produced by what we are launching within the material itself, and then something related to the back wall, reflection. There's a defect, so there's something here, and of course also the echo due to the presence of the discontinuity has a lower amplitude. What's the problem? That there's a problem of resonance. So when you have something that is impinging on this defect and then go back to this surface, there's another discontinuity. This means that the wave can travel again to the defect and go back and so on. So there's a resonance. This means that once you look at your amplitude in time, like here, you will see, for example, with thickness of this point C, you will see the first peak, and then there's another peak, this one, due to the resonance, and there's a third peak here due to the resonance. The peak B produces a peak here, and then another peak, for example, here. So there's a periodicity, of course, due to the resonance of the wave that is flowing through the material that go back, and then again to the defect or to the discontinuity, to whatever you have within your material. So another point is that in case of ultrasonics, ultrasonics cannot propagate efficiently in air. So you need something to couple your probe to the material, to the target. So typically we use oils, water, but also some water gel. So before you can use your probe and make your analysis, you need to prepare the material by using, for example, by the deposition of some gel on the top of your material. Or, as in Leonardo, for example, they have a very big pool where they place their materials, and then they make this punctual inspection of a wing, for example. So a pools filled of water where everything is placed to get the perfect, in this case, immersion of the testing probe and the material itself. The coupling can be normal, as we have seen before, but also with some angular probe. For example, let's say that you want to check a welding between two laminates, that is something like this. If you use something that is normal, you are not able to see in depth the prison of the defect. But if you may use something that has this shape, you can, for example, touch this point and see if there's an inclusion of air, let's say. So because everything go back to your probe, and you can do that. You can move your beam, you can shape your beam to reach whatever you want. Of course, in a range of 35 till 70, more than 80, because above 80 degrees, there are other form of waves that propagate within the material that are not ultrasonics, but are surface waves. Okay, and as I said, so once you define a setup, you should take care of the transducers, the way you are, the setup that you can create, if this is transmission, reflection setup, and so on. The Kaplan that you need to add to your system depends also on what you are investigating. For example, you cannot use water if then your material has some problems with water, and so on. Or this is of course another point of the setup, the pulsar receivers. Today we get some phased array tools. Phased array, instead of, in this case, in any case that we have seen so far, you get some punctual inspection. So you need to take your probe and move it in 2 dimensions, for example, to check a plate. But in phased array, you have a probe that is made of many emitters, not just one emitter. And then the wave can be formed within the material with some laws of forming these waves. And you can scan an interval, a range of points without moving your probe. So you need to move your probe just in 1 dimension. So it's with some, so let's take it as it says, is the difference between a point in the laser and a line. So you can project the line of your laser and you are able to reconstruct all the points or the 3D shape that is below this line. In phased array, you are able, in phased array pulsars, you are able to reconstruct your internal structure in a range of widths, let's say. And then you just need to move in one direction instead of moving two directions. And ultrasonics is typically a way of testing that is differential. So you know what you expect from the specific structures, because there are echoes due to the material, to the structure, to the geometry, and so on. And you compare what you get from the experiments to what expected. In manual operation, it is made by the brain of the worker that is inspecting the structure. He knows that there should be no echoes, or there should be an echo due to the reflectance of the back surface, and so on. In an automatic processing, you need to be sure that you are inspecting a specific point to make a comparison with what expected from, for example, a CAD or something, or an experiment that you have designed before doing your analysis. And there are many calibration plates that are used before you can perform your measurement in order to be sure that you are that everything is within a standard. Okay. So for data presentation, in ultrasonics, as I told you, the first way to represent the data is this one. So you have the amplitude of the wave that you have received as a function of the time. Time means space. This is known as an A-scan. So an x-axis, you get the time or the depth of what you're scanning, and then the y-axis is the amplitude of your signal. Then in B-scan is slightly different. So for example, let's say that you get a brick like this, and the B-scan is this section. So if you have, for example, here, there's a point of amplitude that is higher than what expected, this means that here there's something. And you can move your B-scan through your volume, and then move it and check whether there's something here or something like that. The other way to represent the data is the C-scan. The C-scan is the opposite. So you define typically an interval. Let's use another image. Like this. You define an interval of depth, that means an interval of time where you are focusing, and then in this area collect the maximum, for example, or the average, or whatever you want. You collect let's say the maximum of intensity that you get in this range. This range could be also, it is a range of time, that means a range of depth. This could be also a line, so an infinite range of times, and you can move your range within the depth just to assess the size and the 2D shape of your defect, of what you found from your analysis. And there's a problem, as I told you before, that it requires very, very high skills. So people that manually do this testing should be skilled enough to be sure that they are revealing something. I don't know if you can remember, maybe who is from abroad not, if you remember the tragedy of Viareggio. That was a train that there was a problem with on the railways. That was a train that was traveling with a gas container. And then because of this accident to the train, the gas container explodes and there was, I think, 25 or something like that, deaths of people that were sleeping because it was during the night. And who made the mistake? Well, of course, there was a problem because there was something on the side of the railways that make an hole in the gas container of the train in this tragedy, so in this accident. But who made the error? Who made the error? And who go to the sale for this error? The worker that made the maintenance analysis and checked with ultrasonics that I cannot say in English, in the part of the train that was perfectly okay, and make some reports where he stated that everything was okay. It took something like 25 years of retention, like that. So that's why it is important to make with very high skill. So people has to have very high skill to make some ultrasonic testing, even if this is very well recognized as a standardized procedure for testing materials. What the time? We have just 1 hour, more or less, 1 hour and a quarter. So I wanted just to show you. This is an example of ultrasonics. If it works, no. It's not properly. Just to relax yourself. If you want to take a nap, you can also stay for 5 minutes. And
we have the images of that ultrasonic scan.
Of what scan?
Images, like the peaks. We have the recordings.
Yeah, sure.
So.
And typically okay. Now everything is manual. So there's a screen, and then there's a worker that look at the screen and state whether there's a problem or not. And the screen make the screenshot that I'll show you right now. But there's no way with manual inspection to record what they are scanning. Typically, they make some screenshot and reporting. I report that this desk is okay, or I report there's a problem and I add my screenshot of the flow that I detect.
For the reference.
So for the reference, yeah, because there was a time that I was asking with some of the engineers of the production of train industry, and he said, just to smile, that if your train goes in the sea, that is, I don't know if it can happen, goes in the sea, your train can shipwreck in the sea, but your paper and document should be on the top, should be perfect. This is the point in Italy, that paper should be okay.
Yes.
But even if you have killed thousands of people with your train.
It's a bureaucratic way.
Yeah, that's Italy. Okay, for example,
everywhere.
What? Sorry?
Everywhere.
Everywhere,
Yeah.
you say? Okay. For example, this is a scan of a part. This is the A scan. Amplitude and time. This is the B scan, the section, the transversal section. And this is the C scan. So I'm collecting all data, the maximum of amplitude that I see between these two red lines in the B scan, and I'm showing you the top of the brick.
The surface.
Not the surface, the maximum of the amplitude within these two guys.
Okay.
For example.
The viewing angle is top, from top.
For example. And this interval, that is an interval of depth, means that I'm looking to this interval of time. Is it clear? So, for example, let's say that I'm focusing on this, that is clearly a defect. Okay. What you have here, that I can also estimate, let's say, okay, like this. I'm now making, okay, let's say like this. I'm trying to isolate this defect. For example, here in this interval, there's something from this point that is clearly shown here. So, because I'm looking at this line, this is where I'm placing my surface. So this point seems to be this one. If you see here, there are some periodic spots, for example, like this. These are due to the geometry. So you can see here that I'm placing I'm placing my probe, let's say probe here, and I can see that there are 3 different peaks due to the echoes of the geometry. What is this?
How do you know the geometry?
Because you look at it while you are doing your...
Okay.
So this was a T-joint, something like this. Okay. This was a calibrated plate, so we knew that there was something here. So if you move to this area, this is the multiple reflections. And when you move to this section, there's nothing, but there's the defect. And you get back this that is at the depth that is higher than this value. So that's why here there are some echoes, multiple echoes, and here not, because I'm looking at the T-joint with a normal probe.
Okay, it's overlap.
Yes, sir?
Overlap, like overlap the wide or
for in this case.
Yes.
But because that's this defect.
But it's a standardized defect.
Yeah.
Okay, but what if the geometric and defect overlap each other?
You cannot see nothing. You see the first that you touch.
You cannot differentiate.
But you can use, for example, another kind of probe.
Okay.
Instead of use the normal, try to use something that there's another angular, there's another shape. For example, the angular shape is let's see, this one. The B section, the B scan, is no longer something that is squared, but depends on the angle. Because in this case, you are not changing in angular probe. These are measurements made with the phase array. Let's start with this. In phase array, instead of scanning vertically like this, you scan changing the angle. And then you take these angles and move your probe to get the C-scan. Okay, and the C-scan is not made focusing on a sandwich of depths, but is made looking at the sandwich at the range of angles. Okay, you can use, for example, this data to remove the ambiguities due to the fact that maybe there could be different defects.
Similar to medical sonography.
Well, I don't know. But,
Similar to that.
okay. And I don't know. You have 5 minutes of
Okay.
of break.
Okay.
5 minutes, no more.
This is the window of the model for the audience.
Ah, okay.
So if you draw here, so you can see the focus. So,
But I don't know how I can measure.
okay.
Or maybe
If-
later. Not. I don't know if I will need the blackboard again. But maybe I can use.
If you use the mobile phone, you can
Change it,
simultaneously watch
Yeah, sure.
the window.
Or in any case, I can change, for example, my.
You can also use your mobile phone to see the picture.
No, but I mean, instead of using not using my mobile phone, but use something different to show you my screen, for example.
Like paint.
Like make some
yes,
paint.
MS Paint. Okay, good.
Maybe it could be better.
Se devo andare io un po' prima, solo una domanda, ma per quanto riguarda lo spessore della linea laser, fotometria sto parlando, c'è qualche indicazione quanto, perché ovviamente
Ma tu quanto devi vedere? Perché da là si parte.
si parte da lente?
Perché esistono laser. Noi abbiamo in istituto un laser che mi sembra che fa uno spessore di 200 micron, però è un laser ortografico, cioè ha in testa non una lente cilindrica classica, quella per deviare il fascio, ma una lente ortografica, cioè che fa una proiezione ortografica dell'immagine, come se cioè, la proiezione ortografica sarebbe quella che vedi dallo spazio, cioè le case tu non vedi il senso dell'altezza, perché hai una proiezione, il tuo punto di vista è molto lontano rispetto a te. E questi laser permettono di avere una linea molto sottile, però hanno
L'ordine del...
ripeto, non mi ricordo, però volendo lo posso...
i 5 decimi, ad esempio, probabilmente.
Sì. C'è sempre il di diffrazione, cioè nel senso... non mi far dire una cosa, anche perché poi era pure nel rosso, è anche abbastanza vecchio. Probabilmente potrà essere 50, 70, 5, 7 centesimi. Quindi 50-70 micron di spessore della linea. Il problema è che una profondità di campo di 200 micron dopo sfoca. Cioè, se hai una superficie che ha dei salti, non li vedi perché la linea si sfoca. Questo è il problema delle lenti telecentriche, quelle che dicevo che fanno la proiezione ortografica.
Ok, quindi sono le telecentriche, ok, va bene, se l'avevo visto. No, vabbè, nel nostro caso poi dipende da quello che vuoi ispezione, se l'altezza del layer siamo su 3 decimi, roba di questo tipo. Però
già è fuori la profondità di campo.
perché poi che succede? Quando fai la posizione dell'immagine, banalmente uno fa la scheletronizzazione del profilo che acquisisce, però quella è un'approssimazione di fatto.
Sì, certo.
Cioè, quindi...
Poi oltretutto la telecamera, cioè devi andare a vedere la pixel size della telecamera, cioè quanto è grande il pixel della telecamera, in modo tale da essere certo che quando tu proietti con la tua lente, devi fare il calcolo della magnification fondamentalmente della lente sul piano immagine, devi avere che la tua linea la rappresenti con almeno 3, 4, 5 punti. Qua. Sì, perché se tu vuoi fare qualcosa di un po' più sofisticato, tipo il fit gaussiano, fai il fit gaussiano hai bisogno di almeno 3 punti, se no viene a cagare. Quindi deve essere
la linea deve cadere in almeno 3 pixel.
Cioè devi ricostruire il profilo gaussiano per poter fare un fit. Poi io ti ho detto che il gaussiano, se hai una riflessione fatta bene, se la riflessione crea una coda da un lato più larga rispetto al lato di destra è più cicciotto rispetto al lato di sinistra che è più sharp, è chiaro che a quel punto non puoi fare il fit gaussiano, però è sempre bene ricostruire interamente la linea e ci vuole almeno 3-4 punti per costruirla bene. Il fatto è che poi non tutte le ottiche che tu monti sulla telecamera hanno la capacità di risolvere per quella pixel size. Cioè quando tu prendi la telecamera e vedi che c'è una pixel size 4 micron, mi va bene, perché io so che la mia linea sul piano immagine sarà di 15 micron. 4 micron mi va bene, però devi mettere davanti un'ottica che risolve
che adatta
cioè ci sono tutta una serie di parametri quando disegni uno schema diciamo di profilometria e poi su quello devi andare a mettere il laser. Noi per esempio avevamo un problema simile che stiamo parlando 2014-2015, tanti anni fa, e proprio per questo discorso della profondità di campo avevamo usato un asse lineare. Cioè noi spostavamo tutto il triangolo verso l'alto e facevamo a fasce di 200 micron, in modo tale da fare la scansione per bene, e poi unire i punti con encoder, cioè era pessimo codificato, però è un bello sforzo.
Va bene. Vabbè, in realtà la strumentazione l'abbiamo in qualche modo devo adattare a quello che ho, quindi di fatto perché tra l'altro io ho già fatto acquistare qualcosa perché il progetto stava scadendo e i fondi andavano spesi e quindi comunque anche in base ai tempi abbiamo già acquistato. Comunque mi ritrovo con queste cose perché avevo fatto qualche valutazione, poi magari qualcosa l'ho sbagliata, non fa niente, utilizzeremo comunque. Però ma queste parti qui di profilometria ci sono dei libri che approfondiscono, perché da quello che ho visto io c'è una parte da qualche parte.
Allora, in realtà è un'attività poco di ricerca, quindi c'è poca letteratura primaria, così. Quindi articoli, eccetera. Testi che sono più tecniche quasi commerciali, cioè quasi più apprese dall'esperienza. Cioè non troverai mai un manuale di chi ti fa gli ultrasuoni, perché ci sono i corsi di formazione per il terzo livello e ti fanno, e tu fai il corso di formazione per il terzo livello e hai il tuo, c'è qualcuno che ti spiega.
Va bene.
Va bene, dai. Riprendiamo? Let's start again.
Also, you can use the pointer in presentation because for the
they cannot see the arrow.
Yes.
Ah, okay. The pointer. That's why I prefer to.
No, it's good. It's just a little bit improvement.
So the pointer. Where's the pointer here? You know where's the pointer?
I have last year I attended a class from it's in Poland.
Ah, okay.
It's the NDT testing course. So the professor has made everything online, including lab visit and lab experiment.
Ah, okay.
He's the only one who is adjusting with the camera, with microphone, with the surrounding noise, and with experiment. Only one person do all things.
Okay.
And I feel like I am in physical presence.
So the problem is that you cannot see the screen anymore. I don't know why.
Is in sleeping mode.
But why sleeping? so it was connected. Hmm. Okay, so let's start again. So with active infrared thermography. Let's take this final hour just to show you some brief concept about thermal imaging. So in infrared thermography, you typically get the temperature of the surface of what you are targeting, what you are framing. So the output image is made of a thermograph, made of several thermograms. For example, if we we record the video, and for each pixel of the camera, you are able to find the temperature behavior in time for every single pixel of your image. Then, the principle of thermal imaging was discovered by this guy here, William Herschel, in 19th century, where there was a very important period for light experiments, Maxwell equations, and so on. So using a prism and a temperature measuring equipment, he was able to measure the temperature associated to the wavelength distribution of a spectra coming from stars. And then he discovered also that there's an invisible light, that is the infrared light, where this temperature is much more sensible for the analysis of the black body emissions. So, in principle, you get, so these are the bands of electromagnetic radiation, from gamma rays, X-rays that you have seen before, then ultraviolet rays, the visible spectrum from 400 to 700 of nanometers, starting from the violet to the red. And our peak, so with our eyes, we can see, of course, this visible light. So that's why we call it visible band. And we are able, we have our own respondence to this wavelength. For example, we are much more respondent to wavelength across the yellow instead of red or blue. And that's why, like, when we see at light, we can better work with, can better see with warm light instead of cold light. Cold light is much more used for those environments where you need to be concentrated, because your brain has to adapt the eye to take the concentration, because it's in, let's say, in an uncomfortable state. Okay. Then there's an infrared ray band that extends from these 700 nanometers to so far wavelength, and we see here from near infrared we are till 3 microns, then middle infrared to 3-6 microns, far infrared till 15 microns, and then 100 microns of extreme infrared. Then, of course, there's microwaves and the other electromagnetic waves used for transmitting signals, television, radio, and so on. So, depending on the range that you are focusing, infrared cameras used for temperature measurement can be divided in short wavelength cameras or long wavelength cameras. Okay, and what is the difference between these two cameras? Is the range of temperature that they can detect, because temperatures is related, the range of temperature is related to the range of wavelengths that that are collected. And which is the principle? The principle is the principle of black body radiation. So in black body radiation, assuming that there's a black body with completely opaque, without any reflection, transmission, any way to change the energy out of emission of the actual emission of electromagnetic wave, this radiation of wave of electromagnetic wave. Once this body is in thermodynamic equilibrium with the environment, you can see that there's a peak of your the spectral radiance, depending, and the position of this peak and the amplitude of this peak depends on the temperature of the black body emission. There's also a law that we see here. So, for example, if you use some carbon brick for your barbecue, when they are very hot, they are close to red, and you can see that there's a red, very, very bright red. This means that your temperature is very high. Once they cool down with some hundreds of degrees, you cannot see nothing, because it is not emitting, but it is emitting a different wavelengths that are in the infrared spectrum. And also the amplitude of the emission is darker, let's say, is not so bright as the one that you get with the maximum temperature that you get with your bricks of carbon when you make your barbecue. But for example, if you use your phone camera and you try to make some picture of your barbecue, you will see something close to the violet, because your camera is able to see some wavelengths that are in the real infrared spectrum that you cannot see with your naked eye, even if your barbecue is cooling down. Okay, and the principle is related to the Stefan Boltzmann law. So the radiance from your in a specified angle of view, etc., is given by the fourth power of the temperature. So this is related to the amplitude. But there's also a shift of your wavelength that is seen here from.
You told the example of black body. Black body means it absorbs all the light, or we assume that.
Yeah. It's completely opaque. There's not reflection, no transmission. So
it means that we are only seeing the specific object without any external noise.
A black body. Black body. That's it. So completely opaque. There's no possibility to make radiation for electromagnetic wave radiation, to be reflected, to pass through this object. So there are three components: emission of myself, something that is transmitted by myself, and something that is reflected. Yes. So you are deleting these last two components, and you are assuming just that I'm emitting.
Okay, this is blackboard. This is blackboard.
Perfectly, perfect. Okay. Yes.
So now it is room temperature.
Even if your blackboard can reflect something, okay, it's not perfectly black. Yes. Okay, so it's close to 1.
Okay, so
the emissivity.
So it's not in room temperature.
We are at room temperature, yeah.
It doesn't deal with temperature now. It only deals with color.
Yeah, okay. So, but I mean, in terms of electromagnetic wave, so your electromagnetic wave can be in the visible light and you see it like black. But if you move to larger wavelengths at 15 microns, for example, you will see that it is emitting something that is related to its temperature. Okay. If the temperature is higher, if I take this blackboard and put it at 5,000 degrees, 5,000 degrees, this will be red, and you will appreciate that this is red, like the carbon bricks. So, because the wavelength of your emission moves to shorter wavelengths. Okay, so that's why when you smoke, you can see that your cigarette turns red when you are getting air, because you are increasing the temperature of your cigarette, till you can see that the wavelength is shifted in the visible spectrum. Okay, that's the point. So there's a difference in the amplitude that is made by this formulation here, but also there's a shift in the wavelength. If you are working in a specified wavelength range, for example, let's say that you are just looking at one band, you can estimate the amplitude and say that this is proportional to the temperature. Okay, so there are two ways to see everything. Typically, of course, it's much easier to fix a band and then relate the temperature to what you are gaining from as an emission of a luminance in that specific range of temperature. That means range of wavelengths. Okay, and so that's the point of emissivity. So for black body, there's a perfect emitter. The emissivity is 1. This emissivity is a property of the material. It's not a property of the camera or something like that. It's a property of the material and depends on many factors. Even surface roughness, the color. There are many things that are related to the emissivity. And it's something also that depends on the temperature itself. So the emissivity can change as a function of the temperature. This blackboard can have an emissivity of 1 at room temperature or an emissivity of 0.7 at 200 degrees, let's say. No. Okay, so you typically what you do to get a kind of standardization to paint your target. So you have, or use some targets that are already painted, are black or something like that, just to make everything somehow, let's say, regularized. Okay. And in fact, the emissivity depends on the shape of the object, the thickness, the viewing angle, the temperature, the wavelength. There are many factors that alter this emissivity. Okay, so that's the point. But so we.
Bonjour. Sorry.
Sorry. I'm hearing somebody.
Sorry, it was my.
Can I go on, or do you have any question?
Sorry, it was my mistake. And
Ah,
I
okay.
made a
Never mind. Not a problem. So as I said, in thermal analysis, it is obvious that we will appreciate a lot to have the actual temperature on a surface, specific temp, 36.4 degrees of my cell. This would be, in an ideal world, what I expected. But if all the conditions are preserved, are kept for the specific experiments, even if I measure my temperature and it's 35 degrees instead of 36.4 degrees, maybe it's the same. The point is that I need to keep this parameter constant. Okay, That's the point. So it is true that the emissivity depends on, but we are not measuring the temperature as an absolute measurement. We are, and we will see later, we want to measure the temperature in a relative way. Why? Okay, let's say something about the thermal camera. So you know that thermal camera are able to convert so the radiated lights in something that could be a measure of temperature. This is, for example, a portable instrument. There are many industry companies that produce this camera, for example, FLIR, there are many other. And there could be coolest detector or uncooled detector, depending on what you want to see. For example, cool detector are much more sensitive to some changes of temperature, but are more expensive than uncooled detector, for example. And cool detector are typically used for to get something that is much closer to the actual measurement of the temperature. When you are, for example, in a laboratory condition, you maybe can use an equipment of 150 kilo euros to check the perfect temperature, surface temperature of your specimen. But in actual industrial lines, maybe you are more intended to use something that is cheaper, that even if you cannot have the same resolution and accuracy of your measurement. Detectors can be a single detector, and in that case, you need to move your setup, like pyrometers, for example, or could be matrix of detectors, and this is the case of thermal camera that was actually in the same way like a visible camera or RGB camera or whatever. So the application, for example, in electric engineering, when you get some insulator, you want to see whether the insulator is working fine or there are some connections and you want to see the temperature of those connections to state if there's something wrong within that. In civil engineering, for example, to, of course, again, the insulation of the walls, but even to see if there's a leakage of water in some places or inspections of the roof if there's some rain that is raining in your own. Or for mechanical engineering, when you use thermal analysis during some fatigue test, for example. Because when you do some stress to your structure, maybe there's an alteration of the temperature and you can collect this alteration of the temperature. Or to state whether there are some frictions between points. So for example, here in this is a transmission of a motor, and you can see that if there's a friction within the component, the gears of your motor. In industry, also for manufacturing, for detecting manufacturing failures. And our aim is to use it in aeronautics, but we can also use it in any other kind of industry where there's a quality control process to make, of course, quality control. So thermography could be passive or active. In passive thermography, you're just working without any source. So, for example, in friction analysis, you are just or in the analysis of the electrical components, let's say PCB board, you are looking at your PCB and then say, okay, there's an hot spot in a specific point due to the working condition of your PCB. In active thermography, you are using some source to induce an alteration of the temperature and then collect how the surface temperature is altered as effect of your source. Of course, this is a non-destructive testing. This means that you cannot use fire or any other source that could destruct your material or specimen. So you can use, for example, halogen lamps, flash lamps, microwaves, ultrasonic vibrations, a laser dot that is transferring some power to to your panel. So you need to know which is the melting point of your material, and then tune your source to be far from this melting point, because of course you don't want to distract your structure. So this is a contactless technique. So the difference with ultrasonics, even if they could be very close to each other, also in this case, there's a propagation of heat wave, and once you get some discontinuity within the material, the wave go back to the surface, and then there's an alteration of your surface temperature. And it's quite similar to ultrasonics. The difference is that this is a contactless technique, so there's no contact with your material. So maybe this could be because this could be used in some smarter sense for automation, because you don't need some robotic arm, for example, to put your probe in a specific point. You can use some camera, some lights as is illuminating your sample, and then collect the data and process it automatically. So that's why we are focusing on thermography. If everything is homogeneous, of course, if you are giving some light, some energy, let's say, to the structure will respond accordingly. For example, you are using an halogen lamp of 1000 watts, for example. On this desk, this is at room temperature. Its temperature start increasing till, I don't know, 60 degrees, 70 degrees, lower than the melting point. Then you switch off your lamps and you try to detect how the surface temperature decays. Okay, if everything is homogeneous, your decay is almost regular in all the points of the surface. But if you have a specific defect with a small shape, limited, within the material, the area, the surface above this defect will respond in a different way. So that's why I'm not interested in the actual measurement of the temperature, of the surface temperature, but on the relative differences between what is homogeneous, that maybe is almost everything, and where there's the flow, when there's the defect. So these relative changes are the object of my investigation. And then, using these relative changes, try to understand, to detect the defect, but also to characterize it, to state, so where is it, at which depth. This could be, for example, a point.
So how much deep we can go?
Okay, this is let's say, we can inspect within the material. It depends on the material, of course. We can inspect the materials, but this is a typical subsurface inspection technique. This means that you cannot reach higher depth. So, and that's why it is typically used with, for example, laminates that are made of composite. 10 millimeters, you say?
In millimeters, like.
For example, for a glass fiber polymer, you can get 10 millimeters, 7-8 millimeters of your depth. So this is because if you want to get more, if you want to go in depth within the material, you need to reach higher temperature. And reaching higher temperature, you can start melting your polymer. That's the point. Okay.
And also, there are the range of infrared, like mid-ray infrared or far.
Yeah.
So which?
It depends on which temperature you want to observe. So if you open a camera, there's a data sheet that is giving you the operating range, and so the corresponding wavelengths that is able your camera to detect. So it depends on which, because, for example, in quality control, you can be interested to get some an operating range between 0 Celsius degrees till 100 Celsius degrees. Okay, but there are many other applications where you want to see higher temperature, 1,000, 2,000 of degrees, and you can move at a shorter wavelengths, But anyway, anytime you open a datasheet of a camera, the first line of your datasheet is the operating range for your detector. So the point, it is easy to understand how thermography works. So there are some relative changes of how the temperature evolves in time. What's the problem? That it's not immediate to understand which kind of defect is within the material, because the defect itself, the temperature behavior itself, depends on many parameters. For example, the physical properties of the material, density and porosity, geometrical properties, the size, the shape of the material of your structure, the thermal properties of the material itself, conductivity, diffusivity, specificity, and also the spectral property, the emissivity that I told you before, but also transmission, reflection, absorption, not only of your glass, okay, but also of the defects that is within. So if there's inclusion of some material, say some paper, this could have some reflection parameters that are different of a void of some air, for example, a void of air within the material, a void. And so in principle, these are the equations. So if we look at the cooling regime, so we have that your temperature is higher. Buonasera.
A che punto? Io c'avevo fino a 18 la prenotazione.
18:30 era? Ok, comunque 18:30.
18:30 19.
No, mezz'ora ce la facciamo. Assolutamente. Grazie a lei. So let's say that we are taking our material and we get that all the material is at 100 degrees. And then we are looking at how the material is cooling. So X is the depth direction and T is time. So we are looking only surface temperature. This means that our X is equal to 0. And if everything is homogeneous, this is the formulation T0 T. Okay, so in a semi-infinite isotropic medium, of course. So we are assuming there's just one interface, air and material, let's say. If there's a defect within the material, there's a kind of resonance contribution. So the first term, 1, is, of course, the same of the homogeneous isotropic medium. The second term, this summation, is due to multiple reflection of the heat wave, okay? That is going to the surface and then back to the discontinuity and so on, okay? So if we can represent this profile, the third one, in terms of a plot, a logarithmic plot, where you can see here that black is the reference. That means that is the case of the homogeneous medium. And when you have a discontinuity that is placed, for example, close to the surface, there's an alteration at time of the temperature at shorter time. If the depth is higher, so your defect is much more in depth, the alteration, analytically of course, is observed with reference to the reference, the black solid line, is observed, for example, with the red, the red or the green lines, is obtained at longer time. So this is somehow similar to ultrasonics. Okay. The second plot on your right means that you are not only so in the first plot we were using the temperature densities of the cooling. In the second case, we are using a normalization of this temperature between in a dynamic range between 0 and 1. So this was just for enlarging the difference between the reference signal and what is produced by in a point that has some flow below. So how large can be the area to be inspected? It depends, of course, on the resolution of your camera, the optics that you are using, which is the field of view of your camera, the distance of your camera to the target, but also depends to the number, how homogeneous is the source wave or structure for the excitation. For example, if you have a punctual source, let's say, you will get that perfectly. Normally, you will get the maximum of temperature, and then this temperature, without any defect, will be lower as you are increasing your diameter, your observation diameter, right? How we can solve this problem? For example, with multiple sources. So in order to illuminate your structure more uniformly, or changing your field of view, so looking at a smaller region. And in this case, you can use also one single source. So the advantages, this is an area scan instead of a punctual scan as the ultrasonics, without any contact, very flexible. It is not intrinsically safe. So when you see some xenon lamp flashing on the material, you will get some problem, let's say, at your eyes, just because there's a lot of power delivered to the surface in a very short time. So it's not safe to see those flash lamps while working. Then there are many other points, for example, the emissivity that depends on many factors and so on. But why we are focusing on thermography, as I told you before, because there's the possibility to make a very high automation with this process, much more than what can be done with other techniques. So we can divide active thermography in two different categories, two clusters. Transient pulse thermography, where we are looking at the... Vabbè, ci vediamo lunedì. Comunque, tranne il venerdì, mi sembra che c'è una certa flessibilità con gli orari, perché se vedete fuori gli orari si può anche iniziare prima, cioè se voi avete una necessità...
Alle 6 devono andare via.
E per
è possibile anticipare anche alle 3, quindi fare 3, 6, andrebbe meglio.
Vabbè, adesso controllo su fuori, tanto qua è tutto molto dinamico e ci accordiamo. Comunque, lunedì ci vediamo alle 3, quindi già quello la possiamo decidere noi. Poi per gli altri giorni vedo gli orari e vi faccio sapere sul Teams.
Ok, grazie.
Niente. Altrettanto. And then stationary thermography, where we are not looking to the transient of the temperature in time, but we are looking to how a kind of DC contribution of the temperature. So we are illuminating, and so we are turning on and switch off the lights in a periodic way, in order to get some stationary contribution. And then we just focus on this stationary contribution in, for example, in this case, in locked-in thermography. So flash thermography, a xenon lamp make a flash of high power, and then there's a pro of a very fast experiment because your flash is something that has the size, the duration of milliseconds. And the problem is that first of all, you just have 1 degree of freedom, so you can just set your power of the lamp. You cannot set anything else, not the duration, because it's fixed, it's a flash. And the other point is that there's a very high energy that is delivered in a very short time, and this could be a problem because you can reach very high temperature of the surface, but you don't have time to warm up also deeper regions. So because you are giving all the energy, and also only the surface is turning to 100 degrees. The other regions are not changing the temperature. So there's in this case you are not able to go in depth with your experiments. But the pro is that it's very fast. In milliseconds we are working. For example, these are actual setups where you can see the flash lamps, and this is an example of how the temperature is in very short time is carried from the room temperature of 26-27 degrees to let's say 68 degrees or something like that. And of course, depending on the pixel that you are considering of your metrics of the camera, you can get, for example, the flash event is at time 0, and then now the temperature decreases. If you are in a non-defective region, for example, there's the decrease of the blue line. In a defective region, the decrease is the one of the red line. This is a video of your flash, and there was a defect, a square defect, that one. In the center, actually, there were 2 defects. There's another on top right of this image. And you can understand how there's so that the problem that I told you before. We are not interested in the temperature as an absolute measurement, but to the differences in temperature. So these are actual thermal video from some inspection made in the laboratory of Tiziano.
The dot in the right, top right, is also defect?
No. Let's say, okay, there was
yes.
Here.
Yes.
And then actually there was another defect that is related to this line. There's this like a wrong coupling between 2 plies of the taper. Then long pulse, also known as step heating thermography. So in this case, the difference, we are always looking at how the temperature varies in time, so transient thermography. In this case, what we can manage is also the duration of the excitation. So we don't have milliseconds, but we can extend to seconds, tens of seconds, hundreds of seconds. In this way, we can down, for example, the power and give more energy to the surface, to the specimen that we are testing, let's say in a sweeter way. So just to touch also points that are in depth within the material.
You mean low energy and lengthy time?
Yes. So for example, in this case, this is on the x-axis you get time in seconds. We get that in let's say 100.5, I don't know, seconds. You are increasing the temperature from the room temperature of 23 degrees to 32. So it's smoother, much more smoother than in a flash. And you can also reach, in this case, in in-depth surfaces. For example, in this case, this is an actual measurement. There's a problem here. If you see your decay, well, it's actually kind of exponential. I don't know if this is taken from a defective region or a sound region. Okay. But there are two discontinuities in the decays at 400 and 850. These are due to somebody that was walking and is reflected by the target. So the reflection of the body of the person that was at 36 degrees make the temperature higher of this small gap. So that's the point. It is easy to understand that this technique is better than the previous one because you are able to get in depth, to go to make temperature lower, 32 degrees, much better than 70. Is safer, let's say, also than the use of flash lamps. But the problem is that for 1,000 of seconds, you must ensure that your conditions are always the same, that you are not altering your conditions. So with all the problems that this means. And this is an example of temperature. So there was an heating phase before, and now is cooling, and there are the rows of defects. This is a calibrated specimen made of an array of some flat bottom holes. And let's see it again. Okay, warming and cooling phases.
The rightmost is not a specimen symmetry shape.
Which one?
The rightmost. It's a little dull spot.
There are 5 spots darker in the first line.
Yes.
That means that are cooling faster. Maybe because there's a void. When it cools faster, it means air. And also heat faster. So warm up faster because there's a void there. These are all voids. The difference is the depth at which these voids are. So because these are flat bottom holes. So you are drilling your specimen, not touching the surface. So everything is completely homogeneous from the top. But you are drilling your surface of, for example, reaching almost the surface on the first line, and then stopping your drilling before some millimeters or something like that. And okay, so we have already seen the differences. So the problem, pros and cons are very clear, crystal clear, I mean. In locking thermography, we are producing something, we are in stationary conditions, so we are looking at the steady state. We are using some thermal wave that is modulated, for example, in amplitude by, let's say, a sinusoidal wave or a square wave. Square wave means that I'm turning on and switch off the lamps periodically for many cycles with a specific amplitude, period, and so on. Then, what is important here is that since I'm emitting something that is modulated, for example, in amplitude, and I know how I'm modulating the amplitude of my sources, I can see what happens to the surface temperature and then collect this information, compare it with what I produced, what I generated to illuminate the surface. And once I get this comparison, derive 2 different maps, an amplitude map and a phase map. The amplitude map means how the temperature, the amplitude, the magnitude of the temperature is different because of some discontinuity, some anomaly within the material. The phase map means a delay. So, as I showed you before, in the case of transient, when you get some void, it warms up earlier. And this means that there's a delay. I can estimate the delay and put it in a phase map. For example, this is an example of the lock-in thermography with an excitation with as a sine wave excitation. You can see here there's a problem of inhomogeneous light. So your emission is concentrating in the center of the image instead of to the wall, to the whole surface. And then is pulsing according to a sinusoidal wave. And this is what we get in time, so sampling with some time samples of our video. And taking, for example, I don't know if you can see, there are 4 points in the image for crosses, green, blue, violet, and light blue. So these are the, on top right, you can see your temperature variation. So there's a difference, of course, in the amplitude, and that's the point that you can see on the amplitude map, but also there's a difference in the phase, in the delay, and you can also recognize it in the phase map. What is important is that the amplitude, of course, is somehow crystal clear, so you see very, very well the first line of defects, those 5 points that are there. But we know that there were many other rows of defects that can be seen, not looking at the amplitude, but looking to the phase map. So that's why it's much more important to look at the time delay instead of the amplitude. So you can get more information from the phase map instead of the amplitude maps. And there's another point that in that case, for example, we are exciting our specimen with a specific wavelength, with a specific frequency, a period that is well defined. We can also change this period, this frequency, so we are adding another degree of freedom in our experiment. So the frequency of your modulation. I don't know if you are familiar with radar or not. If you have, if you want to detect something that has a small shape, you need small wavelengths. If you want to detect something that has an higher size, you need higher wavelengths, because you get much more, you have more resolution with higher wavelengths than what you get with lower wavelengths. If you use higher wavelengths to detect something that is very small, maybe you are completely blind to those particles that are scattering sources. This is the same. If you want to go in depth, you need different wavelengths, because you can touch with different wavelengths, different depths of your specimen. That's the point. So you're adding another degree of freedom to improve the discrimination of the depth of the defect. So finally, the problem definition. We will get, this is something that we have already seen 2 days ago. So we have some examples of what we want to understand, that is characterize the defect, for example. And we are creating this data set. So we want to learn from this data that are related, that are more or less the same that we have shown before. These are this thermal video, these thermograms that are signals of temperature in time. We want to create a model and then taking new data, predict with this model, make a prediction and answer to this question. Is this area defective? So this is the definition of the problem that we want to solve in the next lectures. So on Monday, we will see something about the simulations, the constant simulation. I will host you in our laboratory to get, so maybe you can group in 2 or 3 groups to work with with the software and make your own experiments. Once that I show you, of course, how it works. And then, for example, try to change the parameters, try to play with your structure, change the geometry or whatever you want to do to get a parametric sweep of your structure and say how the temperature changes as a function of your defect. Okay. I will send you a mail with the GPS coordinates. And as I told, and as I said, once you are there, send me a message, text me a message on Teams. I will go downstairs and let you in the laboratory. Okay. So that's all. Do you have questions? Was too boring? You already know about non-destructive techniques. I think it's okay.
Yes, sir.
Yeah, good. Okay, perfect. See you on Monday. So goodbye to all of you that are you still there? Maybe yes or maybe no. Bye. Have a nice day.